Hi, everyone. This is Miss Lasar. This is the lecture that you might have missed in class on Monday or Tuesday. This is the lecture that you're going to watch. You're going to take notes on it, and you're going to submit those notes to the Module 23 notes assignment. And that applies whether you have me as a teacher or Mr. Sachs as a teacher. Here's the lecture, and the topic is evidence of climate change and the human role. So the point of this lecture is to help you out of this sticky situation that you might have found yourself in before. Imagine that a friend tells you that they don't understand this whole global warming thing. They haven't learned about the greenhouse effect. They haven't seen any climate science data. Maybe they've heard that scientists, quote unquote, disagree or we're not sure. How would you address this? What would your conversation be like? How would you begin this conversation? What specific data would you use? Which concepts would you explain? This lecture will give you the tools to have that conversation, to have the data, to plan out this topic, and so that you can feel confident that there is no disagreement here. Scientists do have agreement about climate change, the evidence for climate change, and the effects of climate change. So let's start. The first thing that you need to know when we talk about climate change is the difference between weather and climate. Weather is what you experience on a day-to-day basis. It's the short-term state of the atmosphere. Maybe it's 60 degrees and sunny at BCC. That's the short-term weather. You know that weather can vary from time to time, from location to location. It's colder at night than it is during the day. That's a weather difference. It might be colder in northern Montgomery County than in southern Montgomery County, because northern Montgomery County is a little higher up in elevation. And so weather always includes the time and the location. Climate, on the other hand, is the long-term pattern of weather. And when we say long term, there's actually a specific number in mind, 30 years or more. And so climate is the average weather over many years in one specific place. The average climate in Maryland is a temperate climate. The climate at the equator is different from the climate at 30 degrees north and south because remind yourself of that information you learned in Unit 2. The equator has very high insolation and there's a low pressure zone there. There's a lot of precipitation. But at 30 degrees north and south, even though there's still a lot of insolation and temperatures are high, there's very, very low precipitation because it's at a high pressure zone with that descending cool, dry air. So this is important to talk about because sometimes people use instances of weather to try to refute climate change in particular. They'll say things like, we had a snowstorm today, therefore global warming and climate change can't be real. Well, that short-term state of the atmosphere is not the overall climate. And when we're asking ourselves, do we see significant changes in the climate? We're looking at that over a 30-year period or more. So if the data suggests a pattern that is continuing to trend in one direction for 30 years or more, then we can say, all right, this seems like a persistent climate change pattern. Okay, with that in mind, let's answer our first question of this lecture. Is the greenhouse effect real? I would recommend setting up the next section of your paper with this question, and you're going to collect some information to help you answer this question. Spoiler, yeah, the greenhouse effect is real. So the first thing to talk about is what is the greenhouse effect? And this is a recap of some things that you already learned this year. So going through it, check your notebook for that Unit 2 information about what the greenhouse effect is if you need to look at this in a little more detail. But remind yourself how the sun emits UV radiation, and that UV radiation travels through our atmosphere. Some of it is reflected or absorbed by the ozone layer, about 95% of it. Whew, that's really good. But about 5% of it makes its way to the Earth's surface. And there, the UV radiation is absorbed by the surface, warms the surface, and is re-emitted as infrared radiation. It's no longer UV radiation, it's infrared radiation, which we perceive as heat. And that infrared radiation now encounters things like greenhouse gases in the atmosphere that will reflect or absorb that infrared radiation. And so those greenhouse gases will keep the infrared radiation in the lower atmosphere for a little longer. It won't just be re-emitted right out into space, but that infrared radiation will bounce around the atmosphere, maybe go back to the surface of the Earth before it eventually gets bounced out of the atmosphere and back out into space. The key thing here is that the more greenhouse gas molecules we have in the atmosphere, the longer that infrared radiation will be trapped in the atmosphere, and the more significant the temperature, or the higher the temperature will be. Well, that heat will be trapped for longer. You might be wondering, how does that happen? Please watch this cute video.
Are basically the same distance. The Earth and the Moon are basically the same distance from the Sun, yet temperatures on the Moon average an unlivable -18 degrees Celsius. And even deadlier, they range from -170 Celsius during lunar night to 100 Celsius at lunar noon, regularly exceeding both the coldest and hottest temperatures ever recorded on Earth. And while the days and nights on the Moon are about 14 times longer than those on Earth, our planet's relatively fast rotation isn't what spares us from those loony temperatures. What protects us is our atmosphere. By day, it serves as a shield, blocking out the most harmful and energetic of the sun's rays and about 1/3 of the less intense but visible light. At the same time, it traps the infrared radiation, aka heat, radiating out from Earth's sun-warmed surface, keeping us from freezing solid at night. In order for our atmosphere to absorb any kind of radiation, it needs to have some electrically charged particles for passing electromagnetic waves to push around. And most of our atmosphere is made up of gas molecules that don't have an electric charge. They all have a balanced number of positive protons and negative electrons. But some molecules hold most of their negatively charged electrons closer to one side, lending them a lopsidedness that can jiggle back and forth to absorb the energy of incoming infrared rays. For example, water, ozone, and nitrous oxide are all electrically lopsided, so they all absorb infrared radiation. Then there are gases like carbon dioxide and methane. On paper, neither molecule looks lopsided, so it doesn't seem like they should be able to absorb any radiating heat. But in reality, gas molecules aren't motionless. They crash into each other billions of times per second, knocking each other in different directions and also into different modes of rotation and vibration. And it turns out that both carbon dioxide and methane spend most of their time shaking it in electrically lopsided ways, allowing them to absorb infrared rays and help insulate the Earth. Even though many different kinds of molecules can absorb infrared radiation, the vast majority of our atmosphere can't, because it's made of nitrogen and oxygen, which don't get lopsided even when they are vibrating. They're too symmetric. Nevertheless, the lopsided 1% are such good infrared absorbers that they manage to intercept about 90% of Earth's outgoing heat. Each captured ray gets pinged around the atmosphere, and most end up returning to the surface at least once before escaping to space. We don't need to visit the moon during frigid lunar night to know just how important the game of radiation pinball is for Earth. Ice records from our own coldest climate show that small natural variations in atmospheric carbon dioxide produce relatively big changes in temperature. They also show that, compared to the last 800,000 years, the game today is much, much harder.
So there's a couple key takeaways from that video that you should write down. The first key takeaway is that our atmosphere and the greenhouse effect from our atmosphere acts as insulation. And that means that the Earth maintains some heat at night and doesn't get super cold. And during the day, the atmosphere doesn't get super hot. Those are two key details to write down because they keep the Earth livable. They protect us from those extreme low temperatures at night and extreme high temperatures during the day that the moon, which doesn't have an atmosphere, experiences. Another key takeaway is which molecules are able to absorb infrared radiation. It's the molecules that you saw in that video labeled as greenhouse gases, water vapor, carbon dioxide, methane, etc. And those molecules are polar. They have lopsided electrical charges, or they can become induced polar molecules by shifting around, vibrating, and moving the electrons from one side of the molecule to another so that that charge becomes lopsided. The reason that nitrogen and oxygen, that's nitrogen gas and oxygen gas, cannot absorb infrared radiation is because they are not polar and they can't become induced polar molecules either. Here's another demo that we can do easily on Earth to see the greenhouse effect in action. And this is a demo that the science teacher is going to set up. So he's got two bottles, and they're both half full of water. And he's going to expose both of them to a light. This light will be turned on a little later in the video. And he's going to stick a temperature probe in the top of each bottle to measure the temperature of the air above the water. He's also going to seal each bottle so that whatever gases are in the air above that water can't escape. The first bottle will just be water with normal air above it. But the second bottle, he's going to set up in a particular way. All right, there's the first bottle. It's been capped and sealed with a temperature probe. The second bottle, he's going to put a couple Alka-Seltzer tablets into. And as he puts these tablets into the water, you'll see them fizzing. And that fizz is actually carbon dioxide gas that's being released as the Alka-Seltzer has a chemical reaction with the water. You can see all those bubbles, and those bubbles are carbon dioxide gas molecules that are in the water, and then they're going to move up into the air above this water. So this bottle on the left has way more greenhouse gases in its air than this bottle. He's just turned on the light, and it looks like this bottle is more lit up, but that's just because of the camera angle. They're evenly lit. And over here, we can see the temperatures of the two bottles, and they're both at about 21 degrees Celsius at the beginning. And an hour later, we can come back and see the temperature differences. And now there's a really significant temperature difference. The bottle without the additional carbon dioxide is at 31.1 degrees Celsius. The bottle with the extra carbon dioxide is at 44 degrees Celsius, so almost 10 degrees hotter than the bottle without carbon dioxide. So we can see that this bottle with a larger concentration of greenhouse gases is better able to trap the heat from this heat lamp that's being shone on both of them. We're going to give you a couple more examples of the greenhouse effect in action. And to do this, we're going to look at some large-scale systems, planets. We'll be looking at the 3 planets closest to the sun, including our planet, Mercury, Venus, and Earth. And the key thing here is we're going to be looking at the composition of their atmospheres. So Mercury is first. Mercury has a very, very limited atmosphere. Its atmosphere has incredibly low pressure, which indicates that the molecules in the atmosphere are extremely spread apart. It's a very low concentration of molecules. And the composition of the atmosphere is also notable because it's mostly oxygen, sodium, hydrogen, helium, and potassium. None of these are greenhouse gases. There are some trace amounts of carbon dioxide, some trace amounts of water vapor, but very, 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 very low amounts. So this indicates that Mercury does not have a very thick atmosphere. There's also not a lot of greenhouse gases in its atmosphere. We would not expect Mercury to experience a strong greenhouse effect. And the way we'll see that is with the daily high and low temperatures. If we don't have a greenhouse effect, we're not going to experience that insulating effect. So, what are the high and low temperatures on Mercury during a normal Mercurian day? Well, at night, the temperature on Mercury gets down to negative 275 degrees Fahrenheit. During the day, the temperature gets up to about 840 degrees Fahrenheit. That's almost twice as hot as the maximum temperature of your oven. And that wild variation in daily temperatures is because of its lack of insulating effect from the atmosphere. There's just not enough greenhouse gases in the atmosphere to provide that insulation. On the flip side, we have Venus. First thing to notice is that the surface pressure on Venus is super high, which means it has a very thick atmosphere. And its atmosphere is 96.5% carbon dioxide, which, as we know, is a greenhouse gas. So it's got an incredibly thick atmosphere. It's also thick and concentrated with greenhouse gas molecules. We would expect Venus to experience a significant greenhouse effect and significant insulation because of that. Now let's look at Venus's high and low daily temperatures. The mean high temperature on Venus is about 870 degrees Fahrenheit. That's super hot. But the mean low temperature on Venus is only 864 degrees Fahrenheit. So our high temperature for the day, 870 degrees Fahrenheit. Our low temperature is just 6 degrees lower than that at 864 degrees Fahrenheit, another super, super, super boiling hot temperature. So this lines up with what we would expect, because an atmosphere that is totally thick with greenhouse gases is going to experience really strong insulation, not a lot of temperature variation at all, and the temperature is going to stay consistently high because we're able to trap all of that infrared radiation. And now let's look at Earth. What is Earth's atmosphere like? Well, it's mostly nitrogen and oxygen, but then there are small concentrations of water vapor, which is a greenhouse gas, carbon dioxide, which is a greenhouse gas, methane, which is a greenhouse gas, nitrous oxide, and ozone, which are also greenhouse gases. And so we're seeing more greenhouse gases in Earth's atmosphere than on Mercury, but significantly lower greenhouse gas concentrations than we saw in Venus's atmosphere. And so what we would expect is a temperature fluctuation that's not as significant as Mercury's temperature fluctuation, and definitely larger than Venus's temperature fluctuation. And you've been on Earth before. You maybe know what the temperature fluctuation is like from the coldest to the hottest areas of Earth. If we compare these three planets, Mercury has a huge temperature fluctuation. Venus has a pretty small temperature fluctuation. I know these numbers are a little different from the numbers that you saw on the earlier slide. That's okay. The key thing here is that you're noticing that Venus has a really small temperature fluctuation and it's super hot. And Earth has a temperature fluctuation that's somewhere in the middle, with a lowest temperature recorded on Earth of negative 129 degrees Fahrenheit and a highest temperature recorded on Earth of 136 degrees Fahrenheit. So we do see a significant temperature fluctuation, but not as big as Mercury. That's what we would expect. So now we have to ask ourselves the question, we know the greenhouse effect is a thing. We also know that carbon dioxide and other greenhouse gas concentrations in the atmosphere are increasing, and I'll show you more data about that momentarily. So is it actually getting warmer? That's our next section. And again, spoiler alert, yeah, it is. Let's take a look at some data. First, before we look at modern data from right now, we're going to look at really long-term data. These are average temperatures over the last 800,000 years. And so we are right here in a tiny, tiny, tiny little slice that's so skinny that it's hard to see in comparison to this large variation. What I notice on this graph is that large scale temperature fluctuations of about 16 degrees Celsius are pretty common. We see highs and lows, highs and lows. Look at the timing of those fluctuations. Notice how long it takes for those big fluctuations to happen. Maybe 50,000 years, 80,000 years, maybe even 100,000 years. So we do see many repeated fluctuations in the average temperature on Earth, and it happens at a relatively slow pace, with about 50,000 years necessary to see a major temperature fluctuation. Let's look at a bit of a smaller time span, from the year 2000 back to the year 1000, so roughly the last 1,000 years of history. We have average temperature data for most of those last 1,000 years, not from thermometers, but from tree ring data, coral data, ice core data, and historical records. So we can infer what the average temperature was on a year-to-year basis from these indirect sources. Starting in roughly the 1900s, we also have direct data from thermometers. And what you're noticing by looking at this graph is that it looks like temperatures held fairly stable over the last 1,000 years, except for this big increase at the end. And this increase, okay, so this is about a degree. We're seeing about a degree of increase in about 100 years. Now, that's actually a lot faster than we've seen in the past. Going back to this chart, we're not seeing huge increases on the scale of a degree in 100 years. We're seeing increases of a degree on a scale of 1,000, 10,000 years. So increase in temperature of a degree in 100 years, that's very fast. And here, if we look at an even more narrow time span, just the last roughly 100, 120 years, 140 years, this time period where we see this temperature increase of about a degree, if we compare this graph and this rate of temperature increase to some other factors, there's another factor that correlates very precisely in scale and in speed with this increase. And that other factor is atmospheric carbon dioxide concentrations. So as we see temperature increasing, we also see atmospheric carbon dioxide concentrations increasing at a very, very similar rate. And now we need to ask ourselves, does that pattern correlate for all of the time that we can possibly examine? So here we have temperature variation over the last 400,000 years. Underneath it, we have carbon dioxide concentration, atmospheric carbon dioxide concentration for the last 400,000 years. And so now what we're seeing is that it wasn't a fluke. When we saw temperature and carbon dioxide increasing in tandem together, that is a pattern that holds for all of the time that we have indirect records for. When we see carbon dioxide concentration increasing, we also see temperature increasing. When we see carbon dioxide concentration decreasing, very, very shortly after, we see temperature decreasing. And this pattern holds if we look at another greenhouse gas, methane. Methane increases, temperature increases. Methane decreases, temperature decreases. So these are our two greenhouse gases in question. And these two are particularly relevant because carbon dioxide and methane concentrations depend not just on human-caused processes, anthropogenic causes, but on natural forces as well. And that's relevant because you may be wondering, well, were humans on Earth for all of this time? The answer is no. Modern humans have been around for about 10,000 years, maybe 20,000 years. There's some debate. But we've had life on land for far longer than that. And so when we think about what could be driving those carbon dioxide concentrations, we can think about things like decomposition. Decomposition is a process that releases large amounts of carbon dioxide. Anaerobic decomposition releases large amounts of methane. And so one thing that you'll learn about is the patterns that underlie some of these increases and decreases in carbon dioxide, methane, and temperature. For example, let's say we have a major decomposition event and we have a ton of carbon dioxide and methane released. Now those extra greenhouse gases in the atmosphere increase the temperature, and with a warmer temperature and extra carbon dioxide, photosynthesis can increase, and plants can absorb that carbon dioxide at a greater rate, and they'll do that until they've absorbed so much carbon dioxide that the temperature falls as well. And now it gets a little chilly for those plants. And so they have a harder time doing photosynthesis, and maybe some of them die, and then we have another decomposition event and some more carbon dioxide is released, temperature rises, etc. And that pattern continues. That's an example of a natural pattern that can tie together temperature and carbon dioxide. So what about this modern fluctuation, this modern increase in temperature? Could that be explained by natural forces as well? Well, we can look at the natural forces that would impact the temperature. El Nino is known to impact the temperature. So if we separate out just the impact of El Nino Southern Oscillation over the last 120 years or so, what we see is a temperature pattern that should look like this. If the only thing impacting temperature was the El Nino Southern Oscillation, this is the fluctuation in average temperatures that we should have seen over the last 120 years. If we separate out total solar irradiance, how much incoming solar radiation there is, we can also see that we would expect a fluctuating temperature pattern that maybe is increasing a little bit over the last 120 years. And if we look at volcanic aerosols, volcanic eruptions impact temperature because they don't actually increase the temperature, they decrease the temperature. All of the particulate matter that's thrown up, all the ash that's thrown into the atmosphere from a volcanic eruption, that can actually reflect a lot of incoming solar radiation and can cause that radiation to be reflected back out into space instead of warming up the Earth. So we'll see a temperature drop at the times of major volcanic eruptions. And so these dips that you see in the projected temperature, these would be the dips in temperature based on major volcanic eruptions that happened in the last 120 years. So these are the different influences, natural influences on temperature, and altogether, they do not create a substantial temperature change when compared to the anthropogenic, the human-caused forces. This is what the change in temperature has looked like. It's on a larger scale than we're seeing in any of these projections based on natural forces. We see an increase in about a degree, as opposed to a fluctuation from El Nino that should be pretty steady, maybe an increase in a like 0.2, 0.1 degrees based on changing solar radiation, maybe a decrease of 0.2 degrees from volcanic aerosols. That's not what we're seeing. We're seeing a much larger increase in temperature than can be explained from these natural factors. And so this is another graph that sums that same idea up. If the only thing impacting global temperature were natural factors like solar radiation and volcanic eruptions, we would expect to see average temperatures over the last 120 years that follow this green line. But what we actually see is temperatures that follow this blue line. So we've got an unexplained increase in temperature that can't be explained by natural factors and can only be explained by human factors. So now we got to talk about those human factors, those human-induced greenhouse gas emissions. Additionally, if you're like, is it really getting hotter? Yeah, the 10 hottest years on record globally ever in the history of human recording, and based on the values that we can get from ice core data, that we can get from coral records, in human history, the hottest 10 years on record have all been within the last 15 years or so. 2005 is the earliest one. There's 2019, 2016, hottest year on record. I need to check to see where 2020 falls in this, because this visual was made before the end of 2020, so it wasn't considered. Another way that we can see these effects are when we look at ice. So I'm going to show you a time lapse of Arctic sea ice, and you'll notice it will be very clear that there have been some major changes in the amount of ice in the Arctic Ocean and how old the ice is, how long it's been around without melting. So at the start of our time lapse, we're going up north to the Arctic Circle. There's northern Canada. This is Russia. And so the North Pole is like right around here. This is the Arctic Sea, and it's covered in ice. The color indicates how old the ice is. White indicates ice that has been ice for 10 years or more and has not melted in at least 10 years. The bluer the ice, the younger it is. And at the beginning of our time lapse, you saw significant ice cover in the Arctic Circle. We're now in the 1990s, 2000, and the volume of ice is getting a little smaller and smaller. You see more blue, so that's younger ice that might have just formed for a year and then melted in the summer and then reformed during the winter and then melted during the summer. And now we're in 2008 and the volume of ice is much smaller and there's much less white old ice. And we can see significant flow of ice out the Fram Strait. And so if we compare our volume of ice at the beginning of our time lapse in 1987 to the volume of Arctic sea ice at the end of our time lapse in 2000, this is 2010, there's 2012, we can see major decreases indicating that the ice is not able to persist for as long because it's getting warmer. So here's our final section for this video. How are greenhouse gas concentrations changing and why? And how are we measuring them? This is the final section for your notes. The way that we're measuring greenhouse gas concentrations is primarily through ice cores. We can take very, very, very deep samples of ice from the many layers of ice that have accumulated at the South Pole in Antarctica. So think about how that happens. Each year, there's not a ton of precipitation at the South Pole because it's at 90 degrees south. It's a high pressure zone, very low precipitation, more like a frozen desert. But we do have a little bit of snowfall each year. And when that snow falls, it brings down with it all of the gases that are in the atmosphere as it's falling through the atmosphere. The next year, some more snow falls on top of it, and that bottom layer might get compressed into ice. And now, again, that next layer has trapped some gases along with it. The next layer deposited the next year will trap some more gases. And we have these layers building up year after year, and it's so cold that these layers never melt. And so what we have is an amazing record of the composition of the atmosphere at all of these different times in history. And so we can go down to the South Pole, we can dig a really deep shaft, and we can pull up what's called an ice core. And we can break that ice core into layers. And using something like a mass spectrometer, we can determine the composition of the molecules in the atmosphere that are trapped in the ice at different layers. And we can use that to infer the composition of the atmosphere and the amount of greenhouse gases in the atmosphere at different periods in time. We can also use it to infer things like temperature, because there are different isotopes of oxygen. So those are oxygen atoms that have different numbers of neutrons in their nucleus that are deposited at higher and lower temperatures. As it gets warmer, one specific isotope of oxygen tends to form. As it gets colder, a different isotope of oxygen tends to form. And so we can look at the ratio of those two different oxygen isotopes and use that to infer what the average temperature was at that time as well. And here is carbon dioxide concentration data for roughly the last 1,000 years. And we can see that for most of the last 1,000 years, the information about carbon dioxide concentration is coming from ice core data. And then for roughly the last 50, 60 years, we've been able to take direct measurements of carbon dioxide concentrations in the atmosphere by taking samples of the atmosphere and analyzing them directly, instead of indirectly analyzing them by looking at ice core data. And so again, this shows something that is very significant, steady carbon dioxide concentrations for most of the last 1,000 years, with a rapid exponential increase in carbon dioxide concentrations over the last 100 or 120 years. And this correlates with the start of the Industrial Revolution and when humans started burning fossil fuels on a large scale. So looking more closely at atmospheric carbon dioxide concentrations in the near term over the last 60, 70 years or so, we have a chart that looks like this. So this is zooming in for the last 70 years. And this is a specific graph that was generated by taking very direct measurements of carbon dioxide in the atmosphere at many different time points during each year, so that we have a really, really precise and accurate view of how carbon dioxide concentrations on a yearly basis. And what we see is a steady increase. But if we look at each year, within each year, we see an increase, decrease, increase, decrease, increase, decrease, increase, decrease, and these yearly fluctuations in carbon dioxide concentrations. So although the overall trend is a large increase in carbon dioxide concentrations, there's also these yearly fluctuations that we need to be able to explain somehow. By the way, this particular graph is called the Keeling curve, Keeling, Keeling. And it's named after Charles Keeling, who was a scientist at the Mauna Loa Observatory in Hawaii, who was the one responsible for going out and collecting samples of the atmosphere and analyzing them for carbon dioxide. The work has actually been taken over by his son, Ralph Keeling, who's now continuing the same measurements and continuing that oceanographic and atmospheric work. So how do we explain those yearly fluctuations? Well, it has to do with the distribution of land in the northern and southern hemispheres. If we take a look at the northern hemisphere and compare it to the southern hemisphere, one of these clearly has more land. This one, the northern hemisphere, look how much more land mass there is. And that means that there are more plants in the northern hemisphere than in the southern hemisphere, because there's just more land for them to be on. This means that the patterns of plant growth in the northern hemisphere will dictate most of the atmospheric carbon dioxide concentration fluctuation that we see on a yearly basis. For example, in the spring and summer in the northern hemisphere, what's happening? Plants are growing new leaves. They're increasing their rate of photosynthesis, absorbing carbon dioxide, and we'll see carbon dioxide concentrations drop a little bit when it's spring and summer in the northern hemisphere. What happens during winter in the Northern Hemisphere? All of those deciduous trees drop their leaves, stop performing photosynthesis, stop absorbing carbon dioxide, and those leaves actually decompose. And that decomposition will release some carbon dioxide. So we'll see carbon dioxide concentrations increasing during the fall and winter in the Northern Hemisphere. Of course, the same pattern is happening in the Southern Hemisphere, but in opposite. It's just that there's so many more plants and especially deciduous trees in the Northern Hemisphere that this is the pattern that predominates. So again, if we look back at that Keeling curve, winter in the Northern Hemisphere, we see an increase in carbon dioxide concentrations. Spring and summer in the Northern Hemisphere, we see a decrease in carbon dioxide concentrations. And then this overall increase that we see, this is not due to differences in photosynthesis. This increase is due to human emissions of greenhouse gases from burning fossil fuels and other greenhouse gas emitting activities. Now let's look at those. All right, so here are our global carbon emissions, and this is specifically carbon dioxide emissions. So we're going to take a look at this graph and infer what the 4 largest contributors to carbon dioxide emissions are. This black line is the overall increase, where we see what we expect are exponential increase correlating with the Industrial Revolution and burning fossil fuels. And then we can see over time these 4 different major sources of carbon dioxide changing in contribution. Right now, the number 1 contributor to global CO2 emissions, and you should write this down, is petroleum. So that is burning petroleum. And what are we doing that for? Primarily for transportation fuel. We don't burn a lot of oil in power plants. We use almost all of our oil for transportation, gasoline, jet fuel, diesel fuel, etc. But we are burning it, and so we're releasing carbon dioxide because of that. The number 2 contributor to our CO2 emissions is coal. And again, that's burning coal. And why are we burning coal? Well, we're not burning it for transportation. We don't have coal powered trains or cars anymore. We're burning it for electricity generation in coal-fired power plants. Our 3rd largest contributor of carbon dioxide emissions is natural gas, burning natural gas. Why are we burning the natural gas? For heating in buildings and also for electricity generation. And finally, our 4th largest contributor of CO2 emissions is cement production. When you produce cement, you actually have to burn limestone. And when you burn limestone, there's a lot of CO2 that's released. And so construction and the production of cement for construction is the 4th largest contributor of CO2 emissions globally. Now let's take a look at another greenhouse gas, methane. So we see a similar trajectory. We see an exponential increase in global methane levels starting right around the time of the Industrial Revolution. And same deal, we're going to ask ourselves what's causing those increasing methane emissions? What are the largest methane contributors? And now we have an interesting graph to look at. This is kind of like a hybrid of a stacked line bar chart. And the way we can read this is by looking at a particular time point, looking at the height of each color, and the height corresponds to how many million tons, well, not exactly the height, the width of this stripe, how large just this stripe is, indicates the million tons of methane that this source is releasing. And so in 1860, we can see that we've got 3 major sources of methane: rice paddies, livestock, and biomass burning. And when we think about that, this is pretty interesting. Rice paddies release a lot of methane because there's a lot of anaerobic decomposition that happens in rice paddies. Rice is grown in a flooded field, and when you flood something with water, you're depriving the soil of oxygen. And so we won't have aerobic decomposition releasing CO2, we'll have anaerobic decomposition releasing methane. If you're not super confident with that, make a note. Make a note to yourself that aerobic decomposition with oxygen tends to release CO2. Anaerobic decomposition without oxygen tends to release methane. That's why we have a lot of methane emitted behind dams, because there's a lot of anaerobic decomposition in the oxygen poor sediments behind the dam. We've got livestock, and we know that livestock release a lot of methane when they burp, especially cows, and biomass burning tends to release methane. But if we zoom forward in time, we see some other contributors, other sources of methane. And if we look at 2012, It looks like the largest source of methane in 2012 was livestock, again, primarily cattle. The second largest source of methane, and you're noting this, you're noting number one source of methane, number two source of methane, et cetera, just like you did for sources of carbon dioxide. The second largest source of methane is rice paddies. Third largest source of methane is a new one, coal mining. And notice how coal mining and emissions of methane from coal mining have increased over time. We've also got landfills, which are a fairly new contributor. Same deal. There's a lot of anaerobic decomposition happening in the oxygen poor or oxygen deprived environments of a landfill. We also have these two things that are associated with gas production, natural gas production, gas supply and gas venting. These are the methane leaks that we tend to have at natural gas wells. And the final greenhouse gas that we'll look at today is nitrous oxide. And you heard about this one last week in the air pollution lecture. You should be reminding yourself right now or checking back in your notebook, figuring out what nitrous oxide is released from. And be careful, nitrous oxide, N2O, is different from nitrogen oxide or nitrogen dioxide, NO or NO2. They've got different sources and different effects. Nitrogen oxides are irritants, tissue irritants, and they can lead to smog formation and acid rain formation. Nitrous oxide, N2O, is a potent greenhouse gas. And we can see a similar pattern of nitrous oxide levels in the atmosphere as we did carbon dioxide and methane. We see an exponential increase correlating with the start of the Industrial Revolution. And now, hopefully, you've checked what emits nitrous oxide. The primary emitter of nitrous oxide is agriculture. And there's two specific things there: chemical fertilizers and manure both emit nitrous oxide. The key is that both of those, chemical fertilizers and manure, tend to contain a lot of ammonia. And ammonia will actually decompose into nitrous oxide and then will float up into the atmosphere out of the soil that's had chemical fertilizer applied to it or out of the pile of manure. Other major contributors of nitrous oxide include fossil fuel combustion and industrial processes, biomass burning, atmospheric deposition, and human sewage. So same deal, human sewage. That waste contains ammonia that can break down into nitrous oxide and float up into the atmosphere. One other thing to think about is how long each of these greenhouse gases persists in the atmosphere. This is their atmospheric lifetime, or how long the gas remains in the atmosphere. Carbon dioxide tends to remain in the atmosphere for about 100 years, which means that your average carbon dioxide molecule will get released into the atmosphere. It'll bounce around in the atmosphere for about 100 years before it is absorbed from the atmosphere by a plant. Methane will stay in the atmosphere for about 12 years before decomposing, nitrous oxide for about 114 years, CFCs and HFCs about 100 to 300 years. And then we've got some crazy greenhouse gases like sulfur hexafluoride that will stay in the atmosphere without breaking down for over 3,000 years, and nitrogen fluoride, which will stay in the atmosphere for over 700 years without breaking down or being absorbed. And so this is all important to know, because it means that if we stopped burning fossil fuels today, the Earth would continue to warm due to the long-lived gases and the oceanic heat that are already in the system. And so impacts of these greenhouse gases are inevitable. And even if we cut off our greenhouse gas emissions completely today, we're still going to see warming that will not start to decrease for a significant amount of time. So best case scenario, we have a rapid emissions reduction over the next 10 years, and we significantly cut our greenhouse gas emissions to effectively zero. What will the temperature be like at the end of the century? Well, on this map, it's color-coded to show the temperature change in degrees Fahrenheit. And so everywhere, even if we stop greenhouse gas emissions super quickly, we're still going to experience at least a small temperature increase. In the oceans change temperature much slower than land because water is a lot harder to heat up than land. In the oceans, we'll see increases of 1 to 2 degrees Fahrenheit. On land, in the northern regions, especially the polar regions, we may see increases in temperature up to 9 or 10 degrees Fahrenheit. maybe 5 or 6 degrees Fahrenheit across most of the United States, Canada, Eastern Europe, Russia, Northern Asia, etc. So we're still going to see significant temperature increases, even in a best case scenario. But what about not a worst case scenario, but a just the same as what we're currently doing scenario? What if we don't change anything about our rate of greenhouse gas emission? And currently, our rate of greenhouse gas emission is increasing. And so let's assume everything stays exactly the same. It keeps increasing at the normal rate, and we don't do anything about it. Well, at the end of the century, we will see really significant temperature increases worldwide. Across all land masses, we'll see temperature increases of at least 7 or 8 degrees. In our polar regions, specifically our northern polar regions, we might see temperature increases of 15 to 20 degrees. In our oceans, which again are harder to warm up, we'll see temperature increases of about 5 degrees Fahrenheit. That has the potential to cause some major environmental impacts. And that will be the focus of your next class after the Unit 7 test. So this is the end of the lecture. I hope you've taken some fabulous notes while listening. If you need to rewatch any sections, go back and rewatch the section. Make sure your notes are complete, take a picture, and upload them to the Module 23 notes assignment. Thanks for watching, everybody.